Alrighty. G'day everyone. And everyone listening online. You're not ready yet. Okay. I see it's muted.
Can we have a thumbs up from you teamers that you're hearing audio from us and seeing picture?
From you it's great, but from Doug it's not so good.
Alex has got his finger up, so you are hearing us, and you can see the Doug's presentation on the screen. Okay, good, thank you. Over to you, Doug.
Two. All right, okay, thanks. Thank you to Jason, who set me up on his computer. My old Toshi laptop, which is about 11 years old, is not liked by most of the modern service. Such is life. You're okay. Circulators and isolators for the radio amateur. It was about 2004. It's got to be close to 20 years ago. I prepared a short talk for the Brisbane VHF group on nearly the same subject, and I did all the graphics in WordPerfect or Corel presentations application rather than a Microsoft PowerPoint. So I had the remnant of that program, and so I've spent a lot of time and just updated it into what do you call it, Microsoft PowerPoint format. And you might see me shaking my hands and doing all sorts of funny things. So that's what Parkinson's does. So I don't recommend it to anyone. Okay, circulators and isolators. What are we talking about? Here's a interesting one. Start with quite a big heavy chunk. It was actually bigger than this one here and heavier. That sort of. Where am I? Moment there on the. Okay. Anyway, that's the sort of isolator that we're. But this big one here, you look at the frequency. Very unusually, it's what frequency 135 to 150 megahertz, which of course is of interest to VHF operators, and it's a circulator. Here's the actual real life version of it. A little bit smaller. Clearly, it's for 432 megahertz, but it's a circulator as well with end connectors on each. And it makes it's quite a chunky one. Here's one of the only three that I've actually got that are on an amateur radio band. That was exactly on 3.4 gigs. That's a little SMA sized one. Getting down in size. This next one is it's on 10 gigahertz. These three are circulators. Only about 25 mils by square approximately. And here's an unusual one. Look at the frequency band of that one, 45 to 52 megahertz. I acquired this somehow or other a good few years ago. Tried to make something for the 6-meter beacon.
Real.
But anyway, it worked. And we're also talking about something really quite small, only about 15 by 20 mils or something, a little thing like that, which is an isolator, where it's actually a circulator with the load built onto it. So we're talking about something that's fairly small, but there it is, mounted in a 2.4 gig amplifier that I built, about a 40 watt amplifier I built a good few years ago. And where is it? It's there. Looking closer, there is that very same one sitting there sitting in its microstrip sort of position. And here's one picture of taking a circulator, configured as an isolator on the output of the 3.4 gig amplifier of the VK4RBB beacon. Oops. So, do radio amateurs need them? First point. But hardly anyone ever uses them. On HF bands, probably not applicable. There's very little need of them, and I don't know that they make them down there very much. Certainly with the technology that I'll be talking about tonight. VHF, UHF, there's an occasional need. But life can go on quite all right without a circulator or an isolator. The microwave, again, I'd say the same thing, a little bit more, but really life can go on fairly well with just, but they're fun to play with and fun to seek to understand. And I hope that's what this talk can present. First of all, I mean, we amateurs probably get a bunch of isolators and circulators and say, well, I wonder if that works, if I can use it. But when the original people are buying them, they say what frequency they want it on, what bandwidth it needs to work over, what insertion loss, and what power it's got to be able to dissipate. So here's one online purveyor of coaxial isolators and circulators. Notice the frequency near the bottom of the page there. Their frequency range is 25 megahertz to 50 gigahertz. Not all with the same one, of course. And anyway, all sorts of different connectors and things. If you wade through here, you can see on the black writing in the middle of the screen, different octave bands, 2 to 4 gigs, 3.3 to 6, 4 to 8, 6 to 12. And these can be circulators or isolators and other octave bands. And so there's quite a lot of variation, and that's why there are so many available. And you can pick up in various places. What sort of variations are there? Isolators. Well, we're going to talk a fair bit more about that, but the ones I've shown you so far have mostly been circulators. There are two-stage dual design ones. We'll probably be able to think that more clearly later on, but in the output of the 1296 VK4RBB beacon, the whole output, the 8 watts, is running through a dual high power circulator isolator design, and it was originally, just for way of example, it was originally designed or acquired, but was only working on about 8 or 9 gigs, where a lot of commercial equipment works, but it was fairly easy to use magnets to bring it up to 800, what am I saying? Not 8 gigs. 8 or 900 megs, bring it up to 1296.
What you do is just hang magnets around it.
Yeah, glued them on.
Yeah.
They're still there after all these years. And you can have waveguide circulators. Here I've got one here on 24 gigs. Well, not really 24, 18 or 19 or something. But that's got waveguide ports all around. The only one I've got. And there's a variation called a peripheral mode isolator. There's one around behind that screen, I think. It's just there?
Yep.
Incidentally, particularly this one I'm holding in my hand, the stray magnetic fields around them are a bit wild, and it might be wise to keep credit cards and other ID cards away from isolators and circulators. Anyway, we'll talk about that later if we get time. So how do these silly things work? I mean, they're really interesting. But how do they work? What happens? First of all, let's look at a theoretical concept of what happens when a conductor carrying an electric current is located in a magnetic field. Now, from high school physics, you'll know that there's current and magnetic field, and they're at the right sort of angle to each other. That produces force in the current, in the whatever's carrying the current. And that's the simple version of an electric motor. So if you imagine the current travelling in the wire coming in and out of the screen, and a magnetic field coming from the top down to the bottom, with on the different polarities of current and magnetic field, there will be a force generated in that wire to the side, and that is actually how an electric motor works, that you're probably well aware. And if the force is in the wire and the wire can move, then around it keeps going, and then we do some trickery to try and keep it going that way. But anyway, magnetic fields are important in terms of flow of electrical fields and things. Another interesting thing is the Hall effect. If the current is travelling in and out of that bar or flat conductor, and there's a magnetic field present there, top to the bottom, there will be a voltage, a potential difference generated across the width of the conductor. And that is the way a Hall effect device works. There's some quite interesting ones. A few years ago, I was playing around with 30 amp Hall effect sensors that work quite well. Anyway, and before we get on to why we're talking about those, a little refresh on microstrip and strip line transmission lines. Just think of a slab of printed circuit board material with a ground plane on one side and a printed circuit track on the other, of the right size. That becomes quite an effective transmission line, although with a bit more attenuation than the copper one. I mean, a bit more attenuation than on higher frequencies due to losses in the substrate. But anyway, that's called a microstrip transmission line. A strip line transmission line, maybe a little bit unfamiliar to people, is a track sitting in air between two ground planes. Or air usually anyway for a strip line as far as the radio amplitudes go. So we're talking about something like this with two ground planes, and right up the middle of that is a strip line track, which you can carefully make to be at 50 ohms impedance, depending on the sizes of the conductor and the distance from the ground planes. And the connects and RF can go through there, easy, quite easy. So let's get on to a circulator. Here is this is in the middle of every coaxial circulator, as far as I know, of the three-port type we're talking about. So there's a funny Y-shaped centerpiece which ends up being part of a three-way strip line in the middle of the circulator. And there's just on the lower side of that is a thin disc of ferrite material, and just matching that on the other side is another thin disc of ferrite matching material, carefully selected ferrite to have the radio frequency performance where you want the circulator to work. So the efficiency and the usable bandwidth depends on the magnetic field strength and some other things that I can't read there, strength and the type of ferrite. Now look at that, take that little thing and flip it over on its side, and you've got an add some ground planes top and bottom. And now we've got a real genuine strip line assembly. That's the beginning of that. Now what they do is get some of these little magnets. So every one of these circulators and isolators has got magnets in it, and that's potentially quite interesting, especially every high school boy likes to play with magnets. You remember? And I've got hundreds of them around home, and I've also got lots of isolators here that people can have later on if they want. So there's magnets in there causing a magnetic field to be going from top to bottom through that sandwich, the whole sandwich of but particularly with the magnetic field focused and intense on the strip line conductors. And of course, the magnetic field doesn't is kept efficiently with a magnetic pathway from the top back around to the bottom. And so that's a kind of that's what's happening inside every one of these ones that I've got on display here. Now, if I've taken magnets out of these that are about 5 millimeters, maybe 6 millimeters diameter, tiny little ones, and some of them are maybe 10 mils diameter, and some are about 15 or 20 mils diameter.
And they rare earth magnets, Doug?
Yeah, they're neodymium ones. Obviously smaller, and probably what's in some of these smaller and more modern ones. That was in answer to a question. I don't know, I suppose everyone heard Colin's question about new earth magnets. So let's look, what actually, what does the circulator do? Well, so inside that little assembly, which is one of the ones that I held up here, tiny little thing like that, there's that disc that's showing in here. Just think the whole of that strip line assembly. And so we're looking at a little, the core component of these circulators, and it's got 3 coaxial connectors, but you got to remember that in the middle of that sandwich is that they're connected together with those strip line things. Now, we call, it's reasonably arbitrary whether you call port number 1, 1, 2 and 3, or 2, 3 and 1, or 3, 1 and 2 if you like, because they're usually fairly symmetrical. It's only small variations in the way they're made that will lead to small variations between the relationships between the ports. So if we take an RF energy source and put it into number 1, as it passes through the circulator, the field gets tangled up with the ferrites inside, and it gets steered. So the energy you're pumping into number 1 port ends up on number 2 port, and that can be that we can use that for useful purposes. If we put the energy source on number 2 port, it ends up on number 3 port for the same purposes, because it gets steered by the magnetic field in a vaguely similar way to the motor was driving that, and the moving the wire, and in a similar way the Hall effect was being produced. If we put the RF energy into 3, then of course it'll end up in number 1. Usually fairly similar performance each way, it's got a fixed bandwidth and frequency range, and depending how it's made, different levels of quality in the performance of the thing. Now, here's an isolator. That's another one of the ones that don't have that with me here. Maybe it's one in that box. Doesn't matter. I think it's on my workbench at home. Anyway, what do you see the difference there? There's SMA port number 1, SMA port number 2, and what?
3. There's a
The
load.
load.
Little load.
50 ohm line angle.
Yep. So there's, just to remember that disc in there is that whole split line, strip lines sandwich. So if we put for the same, immerse it in a magnetic field, put the RF energy into port number 1, it goes to number 2, of course. Put the RF energy into number 2, and it doesn't go back to a connector, it gets dumped into the 50 ohm termination. And you can't put any RF in the termination. So an isolator is simply a circulator with one port terminated with a transmission line impedance, usually 50 ohms. And the numbering of the ports on an isolator, numbering 1 and 2, is usually just 1 and 2, or input and output. You can find those amongst some of these that are showing on the. For you people online, I've got a whole stack of stuff on the table here. But maybe there'll still be enough interest in there, and you can ask questions, or people could show you later on maybe. So what sort of electrical features? That's sort of how they're working. Bandwidth and isolation trade off with each other. If you want good bandwidth, you've got to sacrifice isolation between ports. And if you want good isolation between ports, you've got to have narrow bandwidth. Sort of, you can't get, there's no free lunch. What's the power handling capability? Well, if you think about a circulator, they're a bit deceptive because there's nothing in there that dissipates very much power. The strip line, if it's working properly on frequency, it's fairly low loss. And there's nothing much else. So many of these circulators, with this one's got 3 end connectors on there at 432, it'll probably handle 50 to 100 watts quite okay, because if there's going to be any power dumped through it, it's going to be dumped in an external load rather than in an internal load. You look at many of these other isolators, that one that was on the screen, or even this one here. Look at the size of the termination on this great big fat isolator. Probably only 1 watt, maybe 5, maybe, don't know. This really little one here, it's configured for microchip assembly. I did show pictures of something like it. It has a load on there which you'd normally think would be about 20 watts or something, because it's externally heat sunk. It's not being dissipated in the device itself. Compare that with, here's the one that disobeys the rules a bit. This one it reads 400 to 550 megahertz, 50 watt coaxial isolator. And the reason it's 50 watts is that it's got a great big heat spreader on the underside here, and that would be connected to something that can dissipate 50 watts if you wanted to rely on it to do that. And that really should go in the 432 VK4RBB transmitter, because I didn't have that when I made the 432, that whole show. I talked about a dual circulated design. What was good about that, the one that's in the 1296 beacon is that the isolation of two of these in series is much better than the isolation of one. And there is some increased insertion loss, but it's pretty good protection anyway. It's been working there for 20 years or more. Now, what can you use these things for? Protecting a signal generator, or maybe you could say protecting a signal generator to save the signal generator, but it's more likely to be making sure you've got an accurate measured result from whatever you're trying to do with the signal generator. If you have no reflected load going back into the signal generator, you might be able to use these to protect a receiver front end, or you might be able to reduce transmitter spuriae from signals picked up by a transmitter antenna. So there's another one I thought it must be on the list. Oh, there, TX and RX switching. I've got some diagrams to show these shortly. So using an isolator, you might just think of there's an isolator sitting in the middle there. If the device under test, being tested by that signal coming out of the signal generator, if it's a bit woeful, fairly bad return loss or SWR looking into the front of it, then there'll be a lot of reflected power coming back into the number 2 port. Remember, the signal's going from 1 through 2 with low loss, going into the device, and the reflected power from the device is coming back out and going into 2 and getting dumped in the little termination. So the signal generator doesn't see that. So important performance characteristics of an isolator are insertion loss and relative isolation. Here's another useful for an isolator located in a transmission line from a transmitter, not a transceiver, a transmitter that all the reflected stuff coming back from the antenna is dumped into the load, the isolator load, just as we spoke before. But what about all the other rubbish, the undesired close in-band stuff and even strong out-band stuff that's picked up by the antenna? If it's a fairly broadband isolator, all of that's going to get dumped into the load as well, a fair bit of it anyway. And the beauty of that is that those spurious signals can get back into if the isolator wasn't there, can get back into the transmitter and play havoc with distortion and intermodulation products and things like that. As long as the isolator can handle. The other situation could be if something drastic, there's like with our beacon transmitters, they're on all the time. So if there's some major mechanical storm thing happens and it wrecks the antenna and the transmitter's still trying to work, technically, if the isolator can handle the full power of the transmitter, all the reflected stuff coming back into 2 is going to need to be dissipated. Remember, is Mike here yet? Mike? Oh, good. Mike was showing me some things he's doing in exactly that area, where making sure that he's got in his EME, 10 gigs EME situation set up, that his amplifier is protected from bad SWR by a circulator or an isolator that can actually handle the full 50 or 60 watts that he's got ready to fire up the moon. It's interesting. I was thinking about that just coming over tonight. Mike's wanting to protect a fair bit of investment in the amplifier, but so many of these amplifiers these days are actually designed to be able to keep operating into extremely bad return loss situations. And we amateurs usually recognise what's going on fairly early. Anyway, interesting. But there is a maximum forward power rating for every isolator because it's got the little termination in there, as they all do. Now, what would you use a circulator for? This is a bit of a funny one here because you could use it a bit like an isolator, but instead of just dumping it into the load, you could actually measure it there and get an indication of measured return loss or reflected power coming back from the device under test. Bit unusual, but the signal generator or the transmitter is being protected in that situation. So would you do this way? This is a bit like transmitter and receiver TX-RX switching without a relay. It may be possible. Got some thoughts about that. Remember here that all downcoming signals are routed to the receiver. So if it's in that situation, there's quite a lot of commercial designs are using circulators as TX-RX switching because they're operating so fast, able to switch so fast. But all the reflected power from there, as well as received signals coming down here and going into the receiver, so the receiver needs to be able to handle all this. Oops. Using the mouse. Also, the circulator needs to be designed to handle the output power of the. Remember, the circulator it's still got if it's a high-powered transmitter, it's still a fair bit of that power is going to be dissipated in the circulator on the way up to the antenna. And if that's a high through power, that's going to be somewhere in the 15 to 20 dB down, which is still in the watts region. Now, some of us like testing RF things and measuring what's going on. What are we going to need? We're going to need a signal source to do this sort of testing. We're going to need a power meter, broadband power meter of some sort. We're going to need directional couplers to be able to find out whether circulators or isolators are working properly. So for an isolator, we're looking at testing insertion loss, particularly, and that's basically from port 1 to port 2. And if you're sweeping this with your signal generator, you're looking for a minimum insertion loss at some frequency in the range where it works, and that'll be close to the optimum frequency for use of that particular isolator. If you wanted to measure isolation, really this is just insertion loss back the other way. So this test signal put into port 2 is supposed to be going into the load, but it's only limited by the isolation level. And return loss is a bit like SWR, looking into port 2. If you look at frequency where return loss is best. So here's another way of looking at this. If you wanted to measure insertion loss of an isolator, that's what you'd start with. This will be your first measurement. Through there, set this to some easy thing like 0 dBm or -20 or something like that, but something preferably -10 or 0. And then take that apart and put the device under test in line there, and then hook up your RF power meter without changing the signal generator or anything. And that will give you the measure, you'll be able to measure the insertion loss. That's what's red here is going to be a little bit less than what's red there. And that will be a measurement of what's going on between that connector and this connector. Measuring return loss, it's got to have a directional coupler. There's a nice broadband one from 0.5 gigahertz to 18 gigahertz. Pretty useful. Come in all sorts of shapes and sizes. This one is, can't remember, 2 to 8 gigahertz. And here's an unusual one. It's 125 megahertz to 250 megahertz. Use it on 2 meters. So if you're measuring the return loss of anything, you need a directional coupler that will work at that frequency. And first of all, you set it up with a 50 ohm termination on one end, and then feed the signal into this here and adjust the RF power meter to be a nice steady amount, -10, -20, depending on the coupling and the directional coupler. And then flip the directional coupler around the other way. And reconnect it all up like this with no change. And now you're able to measure the return loss looking into the device under test. Now, you may need to put a 50 ohm termination on that. So you may need to put it on the device, depending on what the device is and whether that the placing of that load has any effect on the measurement. It may and it may not. So that if you were going to test a circulator, you'd look for an insertion loss between 2 ports. Bother with all the detail. And for each of these tests, if you can, it'd be good if you could look for a frequency where insertion loss is a minimum. A bit like I described before, we can look for isolation between 2 ports. And that's an exhaustive list of what you can do with 3 terminals. Yes, and of course, all of these things get multiplied by 3 because you've got 3 ways of looking at a circulator. And then you could spend your afternoon looking for frequencies where the return loss is a minimum, somewhere in the operating range. And that should be very close to the optimum isolation point frequency.
Do you find that you get peaks at the home?
Generally not. I think it's got to do with the way the ferrite interacts with all the fields that it's subjected to. I mentioned before, people like to play with magnets. And in fact, there's magnets in every one of these, and it's probably more fun to try and pull the things apart and see how they're made, and then extract the magnets and you can play with them yourself, or you can get the grandkids to play with them if you like. But anyway, don't play with them near your credit card. Anyway, if you have a circulator or an isolator that's not quite right in its performance, you may be able to optimize it by trying to change the internal magnetic field by trial and error, placing and then gluing one or more permanent magnets on the outside of the circulator in question. So you, by trial and error, adjusting the strength of the field and the direction of the field inside the circulator. And our friend Gary has just showed me something this evening which I have seen before but I've forgotten, and that is we went right back to that Y-shaped strip line assembly in the middle, very middle of it. Sometimes they make circulators not only with just a Y shape but also a stub on the other side, opposite. So there's actually 6 strips feeding away, 3 of which are as before and 3 of which are tuning stubs. And Gary was able to change the operating frequency of this circulator by changing the length of those stubs that are in the magnetic field in the strip line assembly. So I thought that was pretty clever. Good on you, Gary.
A lot of effort, a lot of time. It's a time-consuming thing.
Yeah, yeah. Wet afternoon is what you need. So you're welcome to come and look by these ones I've got on this side. For the moment, I'm hanging on to them, but for these ones over here, take them and let your grandkids pull them apart, or they're circulators are often attached to things that you buy, and they're many of which are useless. And so these ones over here have real possible use, although I haven't played around with the 24 gig or 17 to 21 gigahertz one that I've got here with waveguide ports. I'm reluctant to try and pull it apart because I think everything slides into the middle. Anyway, I'd like to try and still place magnets on it and see if we can bring it up to 24 gigs, which is quite possible. The magnets will raise the operating frequency. Increasing the magnetic field will raise the operating frequency. I suppose you can, in fact, turn the magnets around the wrong way. And if you're putting 2 magnets in there, they've got to be helping each other, as well as helping the field inside. You can, when you do some measurements, you can actually see the way they hang together. So, a peripheral mode isolator, amazing performance you get out of them. Anyway, this operates. Hewlett-Packard got contractors to make these things for themselves with many of their wideband. This one was extracted from a. This one was made for. Thanks, Andre. This one was made for to cover 2 to 6 gigahertz with a 30 dB isolation between the input and output port. 30 dB. So whatever goes in the output port, 30 dB down at the input port. And that's pretty good for an isolator. You can't get that performance out of one isolator of the other type, because this is called a peripheral mode isolator, and it's got to do with the electric fields being crowded onto one side of a conductor in a bit like a Hall effect, I suppose. And it's quite cleverly made. All right. Okay, so that's circulators and isolators for the radio amateur. If you'd like to ask me any questions, that's okay. I'm not an expert in it, but I just like them. They're fun things to play with.
Well, I'd
I'd like to start with a question, if I may. I actually use an isolator in my 10 gig system between the waveguide preamplifier and the 10 gig transverter. Because without the isolator there, the system takes off and the noise performance goes down the tubes. And the only way I can do it was to put an isolator at 10 gigs between the preamp and the input to the transverter, and it's now perfectly quiet. What inside the mechanical parts of a circulator determines the frequency of operation? Is it the length of the strip line, or the thickness of the ferrite, or the ferrite material? So what actually determines, when they make them, the frequency that they work on?
Good question. If I could,
They may add a strip line, so it would be something to do with the strip line.
yeah, it is to do with that. The it's, if you go back to that strip line, Gary, was that a photograph on your phone, or
Oh, yeah,
I wonder if we
something.
can you sort of walk it around and to show it close up to that camera that's in front of us here?
So,
That, this is the circulator that Gary was playing around with. This is the internal part.
original one. And that's the modified version, which brought it down from 1.8 gigs to 2.3 gigs.
So what do you use that for, Gary?
I was going to use it for deep space. It's one of those projects that got shelved.
Oh, really?
Yeah. So I just narrowed this section of line here, and it tuned it. So just playing
And
around.
you in the direction you wanted, but you did that by trial and error, basically.
Trial and error, yeah. Just cut a little bit off with the tin snips and
Like we do with snowflaking and transmitter. Mind the wire. So, Kevin, in response to that, you can go back up. That one that Gary was just showing us has got, if you think of this particular picture here, for each one of those arrows with a little connector on the end, the center point goes across through the center and it's got a little stub on the other side, so that's why it looked like a bright and shining star. So yes, it's the width of the conductors as they go through the strip line, Kevin.
Yep.
It's the permeability, or the whatever the RF does to the particular ferrite, and it's still governed strongly by the magnetic field. Interesting. Anyone else?
If you turn I guess the three magnets,
Two.
so if you turn them both upside down, would it just work in reverse?
Yes, I think it would work. Actually, I think I've done that. I just remembered something else I was going to say. I did acquire a circulator which appeared to be on 3.5 gigs. And I was wanting to use it on 3.4, but I found that it worked totally around the wrong way. Port 2 was good across to port 1, and port 1 was good across to port 3, and similar. And when I realised that, I just turned it around the other way and used it. But that was not on the output, that was on the input. Just imagine how we have a power amplifier block and a LNA block. You normally need a single pole changeover relay. So on the antenna side, there was a proper relay that was on the driver side and the transverter side, where I had the circulator operating in its TXRX sort of capabilities. Just going back to that TXRX capabilities, How are we going for time? Is it all right?
All good.
If the circulator, this is changing over between transmit and receive. And the way I talked about it before, this would be you wouldn't have all of this here. You'd have an LNA on one port, and the LNA would feed into the receiver port, and this port one would go to the high-powered amplifier, and then there'd be a coaxial relay over here. But this breaks down if one of these ports has got a bad SWR, a bad return loss looking into the port. So it actually needs each one of those to be a good report, good isolation and return loss really at the frequency that you're operating at.
Take the transmitter off. With it running, take the transmitter off and
Yeah,
it'd be fine on a radio link
yeah.
because the RF would be dissipated in the low.
So that's it, friends. Go off and enjoy.